All right, good morning, chemists. We'll finish off the first part of chapter 16. This is the last section that will be on midterm 2, which is next Friday. All 4 practice exams are posted now, so I posted the department exams last night. They're linked in that preparations page, the same place you found all the exams for midterm 1, just on a new page. So that's there for you to practice over the weekend, and today we will cover all of the material that will be assessed on the midterm. So you'll have a full week to practice all those things, all right? I think that's it. And so then this Friday, so tomorrow, will just be a graded activity day, so your last chance to practice everything before our next midterm the following Friday in recitation. All right, so we left off in this section, so we introduced the idea of pH, the presence of H plus versus OH minus in water tells us whether our solution is acidic or basic. We looked at a bunch of different examples using a universal indicator where in the presence of more acid, H plus, the solution turned like that bright orange, but in the presence of base, it turned blue. And so we saw some, typical things we work with in everyday life, like sodas, are oftentimes acidic. A lot of foods that we eat are acidic. So in this section, we'll look at the ways to categorize acids and bases and look at kind of the concepts. So the last 2 sections here covered on midterm 2 are really just concepts. So listen closely. All right, so we first talked about Arrhenius acids and bases, and this follows our typical definition of acids and bases we kept from 1210. Acids have H plus. If there's an H plus in the formula somewhere, that's how we determined whether to use acid naming conventions. So these 2 substances, HCl, HF, they both have H's. When they ionize in water, they produce that H plus. Versus bases, on the other hand, you dissolve them in water, and instead of donating H plus, they actually produce an OH minus ion in water. So that anion, the presence of that anion is the base component. And so this definition is very basic, and it was just based upon observations where solutions that produced H plus, so acids, tended to react with zinc metal and would produce a gas. We can see gases. We can't see H plus because they didn't have indicators back then. Bases, on the other hand, won't react with zinc metal. Instead, they react with magnesium 2+ cation. So when there's hydroxide and magnesium present, it produces a solid. It's essentially a precipitation reaction. So they were able to take all these random unknown samples, react them with either zinc and magnesium, and based upon the observation they made, they concluded, okay, this thing contains H plus, so let's categorize it as an acid, or this thing has OH minus, let's categorize it as a base. So that is our very simplest way to think of acids and bases. So sometime later, we were able to actually understand the formulas and the structures of acids and bases. So in these next 2 categorization boxes here, we're actually going to think about what chemical reaction is happening in water when we add base or when we add acid to water. So the first idea here is Bronsted-Lowry acid-base chemistry, and this is very important in organic chemistry. If there's anything you keep in your back pocket for next year, it's Bronsted-Lowry acid-base chemistry. And the idea that acids and bases, it's all about the movement of that H plus H plus proton in a chemical reaction. So kind of following along with our Arrhenius acids, we know that the presence of H plus indicates it's an acid. But with Bronsted-Lowry acid-base theory, we think about it differently. A Bronsted-Lowry acid is a compound that can a proton can be removed, or we can think of it's as a substance that can donate its proton during a chemical reaction. So if we see here HCl, when this reacts in water, it can donate that H plus to something else. When it ionizes, that H plus can go along with water, all right, to form H3O plus, our hydronium ion that aids to the acidity of that water. So H plus creates that H plus, or sorry, HCl creates that H plus in water. It can react with a water molecule to make hydronium. So we call HCl also a Bronsted-Lowry acid because it can donate its protons. Notice here, HCl is both an Arrhenius acid and a Bronsted-Lowry acid. It's just different ways of thinking about it. HCl can donate its proton, so it's a Bl acid here. Versus a Bronsted-Lowry base, still we're thinking about the movement of H pluses, can accept a proton. So here, a compound that can remove a proton from an acid, or it's accepting that proton from another substance. So a Bronsted-Lowry base is a proton acceptor. So here's just a generic base, so like hydroxide, we can see, yes, OH plus can accept that H plus cation and produce H2O in that case. So it can accept a proton. So that is a Bronsted-Lowry base. So those are the basic definitions of Bronsted-Lowry acid and base, but the important aspect here and concept is, can we give you a chemical reaction and can you identify the Bronsted-Lowry acid or base in that chemical reaction? All right, so, but in order to understand and determine which is your Bronsted-Lowry acid or base, we need to know what chemical reaction is occurring. So this categorization scheme is a little bit more sophisticated because we actually have to have formulas, we actually have to have structures. So here's an example of nitric acid dissolving in water. And so let's see what happens when you put nitric acid in water. So here's just the generic, chemical equation. Nitric acid is a strong acid. I know it's an acid because of that H plus. And so when you put it in water, that H plus goes to that water molecule to make hydronium. That aids to our pH calculation. And then we're left with the nitrate anion. But let's think about how that H plus is moving in this chemical reaction. There's a couple ways to think about it. I like to see, okay, to go from reactants to product side, that hydrogen is making a new bond with the water molecule. We're essentially breaking the bond in nitric acid and making a new bond in this water molecule to make hydronium. That's the chemical form, or the balanced chemical reaction, but we can also look at it on a particle diagram. And of course, this is more sophisticated, that chemists needed to understand what things look like in order to see this happening. So in this second set of pictures, you can clearly see this is your proton. On the reacted side, we're breaking this bond to make our product just the nitrate anion, but then a new bond is actually created between water and that cation. So you can see that new bond right there. So those two pictures are showing the exact same thing. It's just one's with chemical formulas and the other one is actually with a particle diagram, which is easier to actually see the bonds being made and broken. So you can clearly see that nitric acid is the proton donor, which makes it what? An acid or a base? If it's a proton donor, if it's donating its proton, that is a Bronsted-Lowry acid. Also, this is nitric acid, so it's going to behave like an acid. Versus water here, is water donating a proton in this reaction? No, it's actually accepting one. So water is what? A Bronsted-Lowry base, yeah, because it's accepting that proton that we see here. All right, and then here's another image where you can see those bonds being broken. All right, so this OH bond is being broken to donate that H plus, and it's creating a new bond with water that you see right there. So all three of those pictures show the exact same thing. We want to be able to identify what is your acid and what is your base. And just to clarify again, the idea of H plus actually doesn't exist. We are, as chemists, just being lazy, and we know that H plus, when you put it in water, always reacts with a water molecule that is floating around in your sample to make hydronium. So hydronium is actually the true form of H plus, but chemists are just lazy and we don't want to write out all of those letters, but they do mean the exact same thing, all right? They're the exact same thing. All right. Okay, so that is Bronsted-Lowry acid bases. You're looking at movement of protons, H pluses. Okay, H plus donor versus acceptor. So our last categorization still follows the exact same things. Typically, anything that's an Arrhenius acid is also a Bronsted-Lowry acid, is typically also a Lewis acid. But the way we think about the chemical reaction is a little bit different. Instead of thinking about how protons are moving in a chemical reaction, we are actually looking at how electrons are moving in a chemical reaction. But typically, we'll still get the same conclusion. Acids are going to be the acids, bases are going to be the bases. It's just we're thinking about it differently. Right? So a Lewis acid is a substance that is an electron acceptor. It accepts electrons. Right? So again, we're thinking about it differently. While a Lewis base is a compound that can donate a pair of electrons. Right? So this categorization is the most generic of them all. It's so generic that we can describe substances as Lewis acids or bases, even if they don't have H plus present, even if they're not like our typical acids like HCl. We can extend this definition even further. It's most generic, right? So we're looking past just H plus movement, we're looking at electrons. But let's look at a generic chemical reaction, all right, between H plus and OH minus. Which one's the acid and which one's the base? H plus is what, an acid or a base? It's an acid, yes. OH minus is a base. Okay, perfect. So we can actually use Lewis acid base theory here to define which one's the Lewis acid, which one's the Lewis base, and it's still going to fit our definitions of what acids and bases are. So if we think about this reaction, in the generic one, I don't actually have the lone pairs on that oxygen written, but it's important. They need to be there for us to identify what is Lewis acids and bases because we're thinking about electron movement. So here are our two reactants. These two combine to make water. So here's our new bond in our water molecule that's created when we neutralize this thing. So if we think about what's happening in this reaction, one of the lone pairs on that oxygen is making that new bond with that H plus cation. This is where a new bond is being created. So these two electrons in the lone pair of oxygen are the same two electrons that are in the new bond between that hydroxide and that hydrogen in water. So these two electrons are the same as these two electrons. Okay, so in this reaction, let's think about electron movement. What substance is donating the electrons? H plus or OH minus? OH minus is donating the electrons. So based on Lewis acid base theory, that makes OH minus what? The Lewis base, because Lewis bases are electron donors. Right? And so then what substance in this reaction is accepting those electrons? The H plus. And so based upon this definition, H plus would be our Lewis acid. And that still fits exactly with all of our other acid-base definitions, but we just want to think about it differently. All right? H plus is still an acid, OH minus is still a base. It's just we're thinking about that electron movement and where we're creating that new bond in our product side. All right, so so Lewis acid base theory works with all of our previous definitions of acids and bases, but let's look at one that's a little bit different. All right, so here is a reaction between ammonia and BF3. So note how I drew the lone pair that's on ammonia because this is important since Lewis acid base theory looks at electron movement. If you look at this example, it's not really obvious what is donating H pluses if we're thinking truly acid-base theory. But Lewis acid-base theory is so generic, we can extend it past just our typical like HCl acids, HF acids and stuff. So if we think about what's happening in this reaction, the lone pair on nitrogen is donating its electron to the boron in BF3, creating this new bond. So these two lone pairs on ammonia are these two electrons that are creating the new bond between nitrogen and boron. So if we use our same definitions as before, of the reactants, which substance is donating its electrons? NH3. So that would make NH3 the Lewis base. Versus BF3 is what? Donating or accepting electrons? Accepting. So that makes BF3, that entire molecule, the Lewis acid. That whole thing. And see how BF3, does that look like an acid? Does that look like an acid we've ever named in 1210? No. But Lewis acid base theory is so generic it extends past our typical acid base things that we think about in terms of neutralization. So Lewis acid base theory still agrees with everything else that we talked about previously, right? It's just you got to think about electron movement. So these are the definitions you do need to memorize, but do we typically just assess definitions on exams? No, we actually ask you to apply it like these follow-up questions, all right? Where I give you chemical reactions and let's identify what is the Arrhenius acid and base, what is the Bronsted-Lowry acid base, and then what is the Lewis acid and base for all of these reactions. And so what you'll see is that the answers will be all the same for all of them, all right? All of the acids are going to be the same thing. All the bases are going to be the same thing, but it's how we think about it and how we arrive at the answer is different. All right, so Arrhenius acids and bases, it's just the thing that can donate H plus and OH minus. So let me do different colors. Let's do green. I'll do green for Arrhenius acid bases. So here are the two reactions. So we're just focusing on the reactant side. So what substance is donating the H plus? HCl. Yeah, it's like the only thing with an H plus. So I'm going to call that a Arrhenius acid, so AA, because it's donating the H plus. It's the only thing with an H plus on it. And then that would make sodium hydroxide the Arrhenius base, because it has the OH group on it. All right? And so if we kind of extend that to the second reaction, if we look at this here in, actually no, let's just finish this first reaction with all three. All right, so we did the Arrhenius acid for the first one. So now let's do the Bronsted-Lowry acid base for this first reaction. All right, so we're looking at proton movement. So what substance is donating its proton? HCl or sodium hydroxide? HCl, yes, because it is giving up that H plus to make a chloride minus ion. So I will make this pink, I guess. All right, so HCl here is our Bronsted-Lowry acid. And then sodium hydroxide is our Bronsted-Lowry base because it's accepting that H plus. That OH minus is accepting that H plus to make water. All right, and then our last one, Lewis acid base theory. So remember, we have HCl, that is H plus, and then sodium hydroxide is OH minus, and it has all of those lone pairs on it. So Lewis acid base theory, are we looking at movement of protons? Nope, we're looking at movement of electrons instead. So which substance is the electron donor of our two reactants, HCl or sodium hydroxide? It would be sodium hydroxide because that hydroxide has that oxygen with all of those electrons on it. So we see that sodium hydroxide is our Lewis base because we're looking at movement of electrons, and that would make our HCl, the presence of that H plus, our Lewis acid. And so if you see here, of all of our three definitions, HCl is an acid in all three of them. Sodium hydroxide is a base in all three of them. It's just we're thinking about it differently. All right, so let's look at this reaction. This is a reaction between ammonia, water, to make NH4 plus and hydroxide. That's what it looks like is happening. I'll draw those lone pairs on there because it'll probably be important. Okay, so let's do our Arrhenius definition first. So our Arrhenius definition, NH3 would be our Arrhenius base because when we put NH3 in water, it's making this hydroxide. NH3 is a base because it produces hydroxide. In that case, it would, this definition kind of, see the Arrhenius definitions kind of break down a little bit because they're a little bit too specific. If NH3 is our Arrhenius base, you might want to say that the water is the Arrhenius acid, but again, our definition kind of breaks down here, and it's probably not appropriate to call water our Arrhenius acid here. What's better is actually to use Bronsted-Lowry acid-base theory or Lewis acid-base theory because it's more sophisticated. Arrhenius acid-base theory isn't very good at defining acid-base chemistry on a particle level. So let's go back and think about, okay, Bronsted-Lowry acid-base theory thinks about proton movement. This is more robust and can help us define what's happening in this reaction. So if we do Bronsted-Lowry acid-base theory, remember that's movement of H+. Here I've even highlighted that H+ for you. Where is H+ moving? What's donating H+? Ammonia or water? The water is donating the H+. Yeah, the one that I'm highlighting, we see here that that H+ is breaking its bond on water and forming a new bond on that ammonia molecule, right? So that would make water what? A Bronsted-Lowry if it's donating its proton? It's an acid, yeah, so this is our Bronsted-Lowry acid. See how this definition is more robust than the Arrhenius one? Versus, that would make ammonia what? The Bronsted-Lowry base. But does that fit the definition of a Bronsted-Lowry base? Is that what's happening? Bronsted-Lowry bases do what to protons? They accept them. Is that what ammonia is doing in this reaction? Yes, it is. It's making a new bond with H+ to make NH4+. So that would make ammonia here a Bronsted-Lowry base in this case. All right, so that's Bronsted-Lowry. Now let's do Lewis acid-base theory, which looks at what? Electrons. Okay, so ignore the H's now. Now think about the electrons. What is happening? The electrons on nitrogen, on that ammonia, are making a new bond with hydrogen on water, and we're breaking that bond on that water molecule. So nitrogen is doing what with its electrons? It's donating it, donating electrons. So that would make ammonia the what? Lewis base. Lewis bases donate electrons. So this would be our Lewis base, and then that would make water the what? Lewis acid, because Lewis acids do what? Accept electrons, yes. And so if you see all of our definitions match, all of the bases all match up. It's just how we're thinking about it in terms of H+ movement or electron movement with Bronsted-Lowry or Lewis acid-base theory. All right, so that's kind of similar to maybe what you would expect on an exam where we give you a chemical reaction and you have to apply the ideas, concepts of Bronsted-Lowry acid-base theory of how H+ is moving or Lewis acid-base theory of how electrons are moving. But again, you'll probably get the same answer of which ones are the acids, which ones are the bases. We just think about them differently. Okay, so in these two reactions, we only looked at the reaction in the forward direction. All right, so ammonia is a base. We've talked about that in 1210. But the reason, so when we put ammonia in water, it's a base because it reacts with water and it creates this new compound that's not ammonia, it's NH4+, it's ammonium. So these two substances, they're related to one another by the addition or removal of an H+. All right, and so this has a special term. These two substances are related to one another. We call these conjugates of one another, right? When we have an acid and it donates a proton, the thing that's created is called its conjugate base. Versus if you put a base in water and it accepts a proton, then we call that new substance that's created a conjugate acid. So all of these conjugates differ by the addition or removal of an H+. All right, so a conjugate base, and we're going to kind of stick with Bronsted-Lowry acid-base theory for the remainder here. So we're looking at H plus movement, and again, important in organic chemistry as well. When you put an acid into water and it donates its proton, all right, the product that's made, this anion, we call this A minus your conjugate base. Right? So HA is an acid, but if you just put A minus into water, it may behave like a base, because now this A minus can now accept protons if it wants to. So that's the idea here, that this acid and its conjugate base, see how it differs by just the removal of an H plus. Basically, when an acid behaves like an acid, donates its proton, it produces its conjugate base as a product. Versus a conjugate acid is produced when we put a base into water. That base accepts a proton. Typically, this has to come from water. All of this is an aqueous solution anyway. And you create this Hb plus cation, and this is what we call our conjugate acid. Right, so that Hb plus can behave like an acid depending on what kind of base we're putting into water. All right, so again, see how these two things, they differ by the addition of just one H plus cation. And then you see the hydroxide that's made there that indicates that this is a base. All right, so all these conjugate acid-base pairs always differ by just one H plus. All right, here's another example, because the base one, I'm going to point out acids. I feel like people understand acids a lot easier than bases. Bases, I don't know, just tend to be a little bit more complex. So I'll show an actual reaction here of our conjugate acid bases. Here we have ammonia. We're adding an H plus to make its conjugate acid. But at the same time, where is that H plus coming from? It's actually coming from water. All right, so that would actually make water an acid because it's donating its H plus. It's being removed to make a conjugate base here, OH minus. So we actually have two conjugate acid-base pairs happening in this reaction because we have two reactants reacting. All right, so water and hydroxide are related. We have acid, conjugate base, and then ammonia is our base. It has that conjugate acid where you add an H plus. Okay, so let's do some examples, all right? Okay, so let's do these first ones, which I think are always easier. What is the conjugate base of these things? So the question is, okay, we're talking about conjugates. Yeah, we either have to add or remove protons, but we need to make sure we add or remove it correctly. So if we want to produce a conjugate base, this is how I think about it. To make a conjugate base, I need to be looking at this substance behaving like an acid. Acids do what in terms of protons? They donate protons. So I need to ask myself, if this substance donates a proton, the thing that's created is its conjugate base, all right? So a conjugate base comes from an acid acting like an acid. All of these things can act as acids. Acids donate protons. So what are we going to do here? Are we going to add an electron to these formulas, or are we going to, are we going to add a proton to these formulas or remove a proton from these formulas? Remove, because these things need to act like acids. So we're going to, oh, I already wrote it here. We're going to remove one H plus or donate it to something else to form a conjugate base. So what would the conjugate base of HCl be? Cl, that's not it, minus, yeah, so we are removing an H plus. So yes, removing the hydrogen, but we also have to think about the charge as well. So do remember the charge that is involved with H plus. If we're removing a positive charge, then what's left is negative. All right, so what if HCN acts as an acid? It donates an H plus. What is left over? Cn minus, yes. So again, remember charge. H2SO4. HSO4, yeah. So remember here, we're donating one proton, only one. What's the charge? Minus, yes. Aqueous. So you might notice here, we didn't take both H pluses off at the same time. Conjugates only differ by 1 proton. But if you look at the thing that we made here, there's still 1 hydrogen left. There's still 1 proton left. So this substance can act as an acid again, and that's what this follow-up question is. Okay, so if this substance acts as an acid, what is its conjugate? It's going to just be SO4, but what's the charge? 2 minus, yes. All right, so again, these always differ by 1 proton. All right, NH4 plus, donated a proton. What's left? NH3, what's the charge? Nothing, yes, good job. That was a trick. All right, yes, all of these are aqueous. Water, what do we get when water donates a proton? Hydroxide, yes. And then finally, hydronium. If hydronium acts as an acid and donates its proton, what is produced? Just water. All right, so all of these substances were acids. They're all behaving like a Bronson-Laurie acid, donating a proton to produce its conjugate base. Okay, so now let's do the follow-up one. Let's write the conjugate acids of these things. These things will act as bases. Bronson-Laurie acid bases. So they're going to accept a proton. So instead of removing an H+, we're going to add an H+ to that formula. So don't just add the H, you also need to think about the charge. Both of those things are important here. So if we add a proton to Cl-, we get what? HCl. And so HCl is the conjugate acid of chloride minus. HCl, is HCl an acid? Yes, it is. So that makes sense why it would be called its conjugate acid, because HCl is an acid. All right, HCN. Oh, I already said it. It's HCN. Add a H+ to Cn-, we get HCN. So we're basically undoing what we just did. Okay, ammonia is a base. The conjugate acid of this base, we add an H+, and what do we get? NH, how many? 4, and what's the charge? Plus, perfect. All right, the conjugate acid of HSO4- would be H2. Yes, H2SO4, any charge? No. The next one, and this one's tricky, right? Because there's a hydrogen, and so if you're unsure of what conjugate acid means, if I have to add or remove a proton, that one can be tricky because this substance is what we call ampiprotic, where it can be, you can add or remove a proton from this substance. It can actually behave both as an acid and a base. So that would be the conjugate acid there because we're adding H+. While the next one can only act as a base, this is HSO4-. All right, hydroxide, you add an H+, you get water. And then finally, water, if that is acting as a base to make its conjugate acid, what do you get? H3O+. Very good. All right, so all of these things act as bases. You add an H+ to form that conjugate acid. Okay, all right, so let's, so now that we understand acids, bases, and their conjugates, because the idea here is you put all these things in water. It's HCl, HCN, whatever. These are all acids. In the water as well, you have a little bit of base that's produced, all right? These conjugates oftentimes act as bases. Or if you put these bases into water, what you also get is you produce the conjugate acid. These behave as acids. So we need to think about the relative strength of these things, acids and their conjugates and vice versa, so we can draw some trends. All right, so we're going to talk about the relative strengths of acids and their conjugate bases. I always think it's easier to think about things in the acid form, make its conjugate, and think about the relative strength of those. Okay, so we have two types of acids, strong acids and weak acids, right? So we have our 7 strong acids. They have certain characteristics, and their conjugates have certain characteristics. But weak acids, there's a continuum, a spectrum of how weak or how strong a weak acid is. We can have a relatively strong weak acid, or we can have a very weak acid. So let's first focus on the strong acids first, all right? So let's remind ourselves what strong acids are. When you put a strong acid in water, what kind of electrolyte is it? It's a strong electrolyte. So if you write a reaction for a strong acid, which arrow are you going to use? This arrow or the equilibrium arrow? The first one or the second one? Yeah, you're going to just use this one, all right? Because it fully ionizes. Okay, you put HCl in water, there is no reactant left over. You make all products, all right? Strong acids completely transfer their protons in water. You get this kind of arrow. Oh yes, you're right there. That kind of arrow. All right, HCl is a strong electrolyte. So then I ask you, since we determined what kind of arrow this is this reaction reversible? No, it's not, because if it was, I would use the other arrow, right? Okay, so if you put this in water, HCl in water, will you find any HCl in water? No, you're only going to find Cl minus and H plus because we used this fully forward reaction arrow. There is no intact HCl molecules in a HCl sample. It's all H plus, all Cl minus. It's completely ionized. All right? So when you put HCl in water, you create all of this chloride minus conjugate. But the idea here is this reaction fully goes forward, and this reaction does not go in the reverse. So HCl is a very, very strong acid, and its conjugate base, Cl minus, is not a base at all. Yes, we call it its conjugate base, but Cl minus does not behave as a base at all. Remember, what's the definition for a Bronsted-Lowry base? What does it do to protons? It accepts protons. So if this reaction does not go in the reverse, does chloride minus ever accept a proton? It does not. So the definition here is the stronger your acid, the crappier the conjugate base is. So HCl is like the best acid. It's the strongest acid. So the conjugate base that you make is a very, very, very poor base, so bad that it's not even a base at all. So chloride is not a base at all. All right, so HCl is an example, sulfuric acid also an example, nitrate, nitric acid also an example. All of these conjugate bases of these strong acids are not bases at all. They're actually neutral, pH neutral, pH neutral. I always have to clarify, because neutral can mean charge, but here I mean pH neutral. That chloride, if you just put like chloride in water, it's not going to act like a base at all, even though it is a conjugate base of HCl. If you put nitrate in water, since it comes from the conjugate of a strong acid, nitrate has no basicity at all. All right, so that's the idea here. The stronger the acid that you put in water, the crappier its conjugate is in terms of basicity. All right, so those are the strong acids and strong bases. Or sorry, it's just the strong acids. So let's talk about weak acids now. All right, so let's think about like our typical weak acid, HF goes to H plus and F minus. All right, you put HF in water, what kind of electrolyte is it? It's weak, yeah, it's weak because I am trying to tell you that with that equilibrium arrow, right? So when you put HF in water, do you find intact HF molecules in that water sample? Yes, because both sides of this reaction exist at the same time. But will you also find F minus in the water sample? Yes, because it's a weak electrolyte. Some of it ionizes, but not the whole thing. All right, and so our rule still applies here, all right? Well, okay, the rule up here was I put it in this direction. Stronger acid, weaker its conjugate base. But I can also say the opposite is true too. The weaker the acid, the stronger the conjugate base is in terms of its basicity. So since HF is a weak acid, HF's conjugate is F minus. You can see that from the formula here. So HF is the acid, F minus is the conjugate base, HF is a weak acid, F minus is also a weak base, all right? Because HF is weak, all right? So here we see some relative strengths of our weak acids. They're all right here, so just ignore all of the strong things. So here we see HSO4 minus is a relatively strong weak acid on this chart versus like ammonium down here, which is lower on this list, is a weaker weak acid. So it ionizes not as much. So I'll say if we have a relatively strong weak acid, we ionize more, meaning we make more H plus in water. So essentially the forward reaction is more dominating in our strong weak acids versus here, down here where we have weaker weak acids, we ionize less, we make less H plus in water, all right? And we could measure that if we measured like the pH or something. All right, so these are just comparing the acids, but then we can also compare the conjugates of these acids. So if I compared SO4 2 minus and ammonia, for example, all right, so SO4 2 minus is the conjugate of HSO4 minus. And so we can make a relationship based upon the relative acidity of these weak acids and bases, versus ammonia is the conjugate base of ammonium. So we can make a conclusion. If ammonium is less acidic than HSO4 minus, then that makes its conjugates NH3 a stronger base than the conjugate of the other one. The weaker the acid, the stronger its conjugate base. So let's answer these questions, because this is typically how we use these tables on exams. I'm going to point out the last 3 1220 exams I've had, a table like this has been present in the context of some question. So let's see if we can't read this table a little bit. Okay, let's name any acid stronger than HF. Tell me. Any stronger acid. Which one? So what are we, so let's locate where HF is right there. Are we looking for an acid above or below? Above, yeah, so let's just say the one above it. So let's say H3PO4 is a stronger acid than HF, all right? So that means that phosphoric acid will ionize more in water than HF. That if you put same concentrations of phosphoric acid and HF in water, phosphoric acid is gonna have the lower pH because it makes more H plus in water. All right, let's think about it a different way. Let's name a stronger base than PO4 3 minus. So let's locate where that is on the table. But are we going to find PO4 3 minus on this side? Nope, we're going to find it on the other side because it's a base. So it's right there. So what is a stronger base than PO4 3 minus? Has to be, are we going to look higher or lower on this table? Lower, yeah, because base strength increases going down. So here we see hydroxide is a stronger base than phosphate anion. All right, all of these bases are going to be weaker. All right, okay, so that is how we read the table. Let's do another one. Okay, actually the rest of the table, I didn't show the rest of the table. All right, so here we have our strong acids. Then we have our weak acids. But if our acid is so weak, and it's basically not an acid at all, that's down here, all right? These substances barely donate their protons at all. Okay, they'd rather keep their protons. But if we think about the conjugates of these substances that aren't acids at all, their conjugates are actually really good strong bases. All right, so because the idea here works again. A substance that's a really strong acid has a really crappy base, conjugate base. So if we have something that's a really crappy acid, its conjugate base is going to be really good. And that's what we see down here. These substances that are acids, if you think about them donating a proton, they typically don't. But if you draw out or work with their conjugates, these substances are going to be really good bases. They're going to really readily accept a proton, all right? So yeah, the conjugates of non-acids, things that aren't acidic at all, are going to be very strong acids. And that's why we see hydroxide here and some other substances that are very, very strong bases and accept protons readily. All right, so that's how we read this table. Okay, so let's do more table stuff, more concept stuff, putting it all together. Make it harder exam-like questions. Okay, so let's use this table. So the big idea is the stronger the acid, the weaker and the crappier its conjugate base is in terms of basicity. If there's one thing you pull away from this, versus weak acids, things that are really poor acids actually have really good conjugate bases in terms of their basicity. All right? Okay, so based upon this graphic, which is the stronger acid, H2S or ammonium? Are you going to look at the red side or the blue side? Since I'm asking you acidity, I'm going to look at the red side. So what is the stronger acid? Can you not see it? So here's H2S. I'm looking at the acid side because I'm looking at acidic behavior, H2S, and then ammonium. So which one's the stronger acid? One or two? The first one or the second one? The first one, yes, because it's higher on the list. Perfect. All right, so which one is the stronger base? It would be, so let's locate, so there's H2S, and then ammonia is right there. Perfect. So which one's the stronger base? Oh, sorry, my hand. Here, ammonia would be the stronger base. Perfect, right? So that's how to read the table. But here, let me ask this question a little bit differently. What if I only gave you half the table? Could you still answer it? So let's see if I can't do this. Okay, what if I only gave you half the table? Could you still answer this question? So let's do the first one. Which one's the stronger acid? Yeah, now the question's harder. Because do I give you acids? Nope, I give you bases. But can we make a conclusion about the acid if I give you the bases? Right? So here are the acids. I'm giving you the conjugates of all of the acids. So you can undo it. You have to look for, on the base side, the conjugate base of both of these. So let's get, what is the conjugate base? Because I'm giving you the bases. What's the conjugate base of H2S? HS minus. That's the conjugate base. What's the conjugate base of ammonium? NH3. Am I going to find these acids on this table? Sorry, this one right here, the blue side. Am I going to find H2S and ammonium, these acids, on this table? No, you're not. These are bases. You look really hard. You're not going to find these two substances, H2S and NH4 plus, on this table. What you will find are their conjugate bases. So this is what we need to look for. Look for H2S minus and ammonia. Right there. Those are the conjugate bases. So of those conjugate bases, which one's stronger? The stronger one would be ammonia, NH3, because it's lower on the list. So that makes the conjugate acid what? Stronger or weaker than the other one? Weaker. Yeah. So to answer the question, in this form, the stronger acid would be this one, H2S, would be the stronger one because HS minus is the weaker base. See how I made the question, I don't know, 10 times harder by only giving you half the table? Yeah. Do you want to do the second one also with half the table? Yeah, let's try it. All right, so hopefully you don't remember what the answer was. Okay, let's just move you over here. Okay, so let's do it with half the table now. All right. Okay, so which one is the stronger base? Are we going to find these substances? These are bases. Are we going to find them under the acids under here? Are we going to find them? No, these are bases. These are acids. So we can't look for these substances straight on this table. We need to think about, okay, these are the conjugate bases of these acids. So why don't we write out what the conjugate acids are of HS minus and the other thing are? And then locate those on the table because that's what we can find. So what is the conjugate acid of HS minus? H2S, and then what else? NH3 would be NH4 plus. Are we going to find these conjugate acids on the table now? Yes, we will. So let's locate where those are. H2S is right here, and then ammonium's right there. So if I'm looking for the stronger base, I'm actually looking for which kind of conjugate acid, the weaker one or the stronger one? The weaker one. So which one is the weaker conjugate acid? Ammonium. Ammonium is the weaker conjugate acid, so that makes ammonia the stronger base. Yes, so there we go. So it would be that one. And was that the same answer we said before when we had the full table? Yes, it was. Yes. Okay, so let's do a little bit more now. Okay, so I'll show you the whole table now. What were the answers? I think it was this one, and then which one's the stronger acid? This one? Okay, all right. So let's do it a little bit differently, but now I'm going to give you the full table. Identify which of these equilibrium lie to the left or the right. So if you notice here, I have 3 different reactions, and they're basically neutralization reactions. I'm taking an acid, and I'm combining it with a base. Right? The table I give you contains acids and bases. So we need to figure out which side of this equilibrium is more dominant in this kind of neutralization reaction. So my strategy for these kinds of questions, basically I'm making an acid and a base fight one another, and we're trying to figure out who wins. And so the strategy here is look on both sides of the reaction, find the pair of acids and bases that are the stronger pair. All right? Strong acids ionize more. So whatever side has the stronger acid-base pair pushes the reaction to the other side. All right? So that's the strategy here. I've written it up there. Okay? Look for the strongest acid-base side. That side wins and pushes the reaction to the opposite side. The idea is like, okay, if you put HCl in water, all right, HCl is a strong acid. It completely wins. And so what you produce is hydronium and Cl minus. In this reaction, the product side completely wins because HCl is a strong acid and ionizes the most. It has the most forward direction arrow, and that's what we're looking for here. All right, so let's look at this first example. So if I react HCl and ammonia, and then I get chloride and ammonium, where does this equilibrium lie? I always like to look for the strongest acid-base pair. You could probably figure out what is the strongest acid-base pair without even looking at the table, because HCl is a what? It's a strong acid, yeah. All right, so we have a strong acid combining with a weak base. Chloride is not even anything, it's neutral, and ammonium is a weak acid. So here, HCl is the strongest component. It's going to push the reaction in the forward direction. So in this example, the product side is most dominant at equilibrium, right? Whatever your strongest component is pushes the reaction to the other side. And so in this case, HCl is the strongest acid. Ammonia is also a weak base. So, and it's the only base that's on this table. So both of those things push the reaction in the forward direction. All right, so let's look at the second one. This one we actually probably have to look at the table. I like to look at the acids because it's easier for me. So in the forward direction, which thing is my acid? H3O plus or F minus? What is my acid? It has to be H3O plus. What's the giveaway? Yeah, there's the only thing with hydrogens, yes. Okay, what about this? H2O and HF, which one is my acid? HF is my acid, perfect. So I want to compare the acidity of H3O plus and HF and figure out which one is the stronger acid, and then that's how I can figure this out. So thankfully, if I'm given the whole table, I can locate where those are. So I have, oh, do I have the wrong answer? HF. Oh, I do have the wrong answer. Whoops. In the corner, okay, so just ignore this in the corner. So let's locate where those acids are on this table, and we see HF is right here. And we see H3O plus is right here. And so we see that the stronger acid is H3O plus, so this reaction should go into the forward direction, so the right direction, right? Because H3O plus is the stronger acid here. All right. We can also look at the bases as well if we want to. So here, if we inspect the bases, F minus is right here on the graph. Water is right there. And again, F minus is the better base, so it's going to push the reaction in the forward direction to the right. Sorry, my answer in the corner was wrong. All right, so let's look at the last one here. What is acting as our acid on the reactant side? H2S or NH3? H2S is our acid. Then what is our acid on the other side, on the product side? So if we think about the reverse direction, what is donating its proton to make our reactants? It would be ammonium. Or you can think about it this way. H2S is our acid, so HF is our conjugate base. So if that's our acid, ammonia is our base, so that would make NH4 our conjugate acid. So what we want to do is compare the strengths of the two acids and figure out which one is stronger here. All right, so let's look at the acid form. So there's our acid, there's our conjugate acid. Locate them on this graph. And so we see that H2S is right there on this graph. Ammonium is right here. All right, so which acid wins? H2S, so this reaction also goes into the forward direction. There we go, all right? And you can expect the bases as well, and you'll get the same answer, that the stronger base would be ammonia, not HS minus, all right? So that is how we inspect how an equilibrium, if we react an acid and a base, where that equilibrium lies there. Okay, so that covers the conceptual parts of midterm 2, all right? So that concludes midterm 2 material. And so we got 25 minutes. So we will continue on with midterm 3 material. So just to reiterate, midterm 2 will cover pH calculations for only strong acids and strong bases. So we can make an assumption that all of the H plus or all of the OH minus comes from the substance that you're dissolving. Now we'll move into weak acid, weak base calculations and how it's a little bit different, that we can't make that assumption because weak acids, weak bases don't completely ionize in water. And then the last part of the chapter was the concepts, Arrhenius acid base theory, Lewis acid base theory, and using this table is the last part and the more conceptual part. So because we finished midterm 2 material, the first homework set is due for chapter 1. That's all the stuff that's covered for midterm 2. This second homework set won't be due until after the midterm. I already changed the due date on mastering. So you just have one homework set due on this Monday at midnight. All right, so let's now talk about weak acids and weak bases. Let's remind ourselves, a strong acid has what kind of reaction arrow? Just forward, yes. They completely ionize. Versus a weak acid, what can you use as just a straight arrow for HF? Nope, you gotta use an equilibrium arrow. So if there's an equilibrium arrow, that means that weak acids have a K expression. Do you remember that from chapter 5? Things with, I hope you do. I hope you do. All right, because you'll be assessed on it very soon here. Weak acids and weak bases follow chemical equilibria, so they have their own K expressions as well. Thankfully, they all follow the same form, all right? So they all have K expressions, they all have K values that you can look up, but specifically we call them Ka or Kb values because they are related to acids and bases. So here's an example of a just generic weak acid, so HF, you put it into water, and you get some H3O plus and F minus. H3O plus is how we calculate pH. But again, does HF fully ionize? If I put 1 molarity of HF in water, will I have 1 molarity of hydronium? No, I won't, because this is an equilibrium. If HF was a strong acid, it would be, but not for this example because it is an equilibrium. So the idea here is in order to figure out what the concentration of H plus for pH calculation is, we need to use the K expression. So let's write the K expression for HF, this acid. Here I have it reacting with water, but we can also simplify it by taking the water out because, again, chemists are lazy and we don't want to write water out all the time. We can write the Ka expression for this simplified version that doesn't have water in it. We still get the same answer here. So we see K. K expressions are always what over what? Products over reactants. It's no different. So what goes on my numerator? H plus, F minus, over HF. No different than chapter 15. All right, products over reactants. If you write the K expression for the first one as well, you'll get the same thing because water is not in the expression at all. All right, and so you can look up the K value for Ka for HF. We're just taking Kc and we're turning that C into an A because this is an acid, right? So you can look it up and you'll find that the Ka value for HF is like 7 times 10 to the negative 4. So based upon the magnitude of this K value, what is more present at equilibrium? The denominator, yes. The denominator, lots of HF. That HF doesn't ionize that much in water. Okay. So weak bases, same idea, follow an equilibrium because we have this equilibrium arrow. We can write the Kb expression for ammonia acting like a base. Ammonia acts like a base when it reacts with water. So in this example, we need water to be here, all right? Bases act like bases when they accept protons. So we have to write the reaction for that. So ammonia grabs a H plus from water to make ammonium and hydroxide. This is the expression, the Kb expression for ammonium, because it's ammonia acting like a base. It's accepting a proton. So, just like before, what is the K expression for this reaction? Concentration of NH4 plus, how did I get that? It's a product. What's the other product? OH minus over NH3. Anything else in the denominator? Do I put water? No, you don't, and that's it. So that is the Kb expression for ammonia acting like a base, right? Okay, so what you notice here is, again, we can't assume that all of the H plus is ionized in water when we put these things into it. So if we want to calculate pH, we need to actually figure out, oh, what's that value in the Ka expression? Or if we want to calculate POH for a base, we need to figure out how much OH minus is present using the K expression. We got to use an ICE table, but it's no different from chapter 15. So we'll talk about that here in a second. All right, so like I mentioned, you can look up Ka, Kb values for any acid and base. Their magnitudes have meaning, all right? Because the idea here, if we look at, let's go look at HF, all right? So I asked you, okay, K is pretty small for this number, or sorry, for this acid, so like, you know, times 10 to the negative 4. That's a pretty small number. So HF, the denominator is mostly present. So if we had a strong weak acid, Strong weak acids have very low pHs. They are acidic. They're very acidic, right? So if we have a weak acid that's relatively strong, it's going to ionize more. It's going to make more product. So how will its K value be different? It'll be bigger. It'll be higher, yes. So acids that are strong weak acids have larger K values, while the weakest of the weak acids have very small K values because they don't make a lot of acid, H+ in water. And so these are what these numbers mean when you look them up. So here we have a bunch of Ka values for a bunch of example acids. So we see here chlorous acid, HClO2. It has a Ka value of times 10 to the negative 2. Versus, let's look at acetic acid. All right, acetic acid has a Ka value of times 10 to the negative 5. Both of these are weak acids, but one of them is the stronger weak acid. Which one's the stronger one? Chlorous acid or acetic acid, based upon the K values. Chlorous acid will be the stronger weak acid because its Ka value is greater in this case, all right? So the idea here is that if K is large, you make a lot of H+ in water for that weak acid system, right? So here, like these two substances are times 10 to the negative 10. These are extremely weak acids that you're barely going to make any H+ in water when you stick it in water. So these are extremely weak acids. All right, so a strong weak acid has a large Ka value. And again, that comes from the products over reactants idea. And acidity is tied to that the concentration of H3O+ that's in the numerator. All right, but do you like to write scientific notation? No, we don't. All right, so instead of reporting Ka values, if you Google like acidity of something, some acid, you might not find a Ka value. You might find what is a pKa value instead, because they're easier to read. But based upon our rules we learned earlier, pKa is simply negative log of the Ka value. And that's what you see right here. So pKa is what you might look up a value for in a textbook or something, but pKa values are just an easier way to represent these very, very small Ka values, where I just take the negative log of the Ka to report pKa instead. All right, so the trend is here that chlorous acid, our strongest of our weak acids, has a very low pKa value, versus over here, phenol, which is a really crappy acid, has a really high pKa value, and it's not very acidic. So the trends are a strong acid has a large Ka value, but a strong weak acid has a small pKa value. So for example, like Ka could equal 1 times 10 to the negative 2. That's a pretty large number, but that same pKa would be 2, which is a low number. Right. So those are the trends. All right, so how we use Ka values. Okay, all right. So let's do a calculation involving a weak acid. But don't be scared. It's just like chapter 15. It's literally no different. It's just for an acid, all right? So, of ice tables, there's 2 ways I can ask you ice table questions. The first way is the Sudoku method, where do you have to use the quadratic formula? No, you don't. Where I give you initial concentrations, I give you a hint at the equilibrium line, and that hint allows you to fill in the rest. So then you can calculate K, and that's what this first question is, all right? So here, I tell you, a student prepared a solution of formic acid and found its pH to be this value, all right? pH equals 2.38. Calculate the Ka of this acid. This is a type 1 Sudoku method ice table. It's literally no different than chapter 15. But here's I have a pet peeve. I hate this word. I copied this out of the textbook, all right, found. This student found its pH to be this. Right? Now that you guys are smarter, you're more comfortable in lab, I want to make sure that you're communicating your ideas correctly in a way that doesn't sound weird. So we don't find data, we don't like find measurements, because it makes it sound like I found it in a drawer, like, oh, okay, like, yes, there's its pH, all right? It's under here, I found it. I hate that word. We don't find measurements. We don't find data. It would sound so much better if I wrote and measured, if this student measured its pH and it was 2.38. Doesn't it sound so much better? And then it gives you credit for it. Not like you just randomly opened a drawer and found its pH. So just be very careful with your language and give you credit for what you did. You don't find data, you measure it or you calculate it, you know? So just a pet peeve of mine. Small thing. Okay, so let's do this. So let's do the ice table. So here is a generic, or here's the Ka expression. But we can also just write a generic K expression here. We can just write HA goes to H plus plus A minus. This is just a generic Ka expression. All right, because this is a weak acid. And so remind ourselves that Ka for this expression is equal to H plus concentration times A minus concentration over HA concentration. Right, products over reactants. So let's ice table this. All right, let's take the information. So this student prepared 0.1 molarity formic acid. So that's HA. But it's HA in which line? Initial, change, equilibrium. Where do we think it goes? Initial, yeah, so we put 0.1 right there, 0.1 molarity. How much H plus and A minus do we have? Probably 0, yes. Does this look any different than chapter 15? Nope. So which way does this reaction have to go? Forward. So the change line is minus X, plus X, plus X. It's just like chapter 15, but it's easier because the stoichiometry is always 1-to-1. Change line is always 1-to-1. Okay, so at equilibrium, what do we have? We have 0.1 minus X amount of HA. We have X amount of H plus and X amount of A minus. All right? Okay, so we built our ice table. All of those expressions can go into our Ka expression if we want. All right? So what piece of information do we not use yet? The pH, yes. So here's the tip. If I give you a pH value, that represents the H plus concentration at equilibrium. That's your hint to the equilibrium line. So can we figure out what X is? Yes, because I give you pH. pH is equal to 2.38. So that means the H plus concentration, oh my gosh, stupid pen. The H plus concentration at equilibrium is equal to what? 10 to the negative 2.38. All right, so when we undo that pH concentration, that is the H plus concentration at equilibrium. Can we figure out what X is then? Yes, because what is X? Based upon the ice table, X is the concentration of H plus at equilibrium. So whatever this answer is X. All right, there's your hint to the rest of the ice table. So now do we have enough information to calculate K? Yes, because now we know what X is. So we put that value. Did I actually calculate it? I don't know. Did I calculate it? Nope, I didn't. Cool. 10 to the negative 2.38. So H plus concentration at equilibrium, which is also equal to X, is 0.00417 molarity. All right, and so we just plug in those values into our equilibrium line and shove it into our K expression. So when you do that, so that's the hint that you needed, Ka is equal to 0.00417 squared over 0.1 minus 0.00417. Right? So for type 1 ice tables, I asked you, do you ever have to do the quadratic? No. Do you ever make an approximation in a type 1 question? No, we never make an approximation. Because you might be thinking, oh yeah, why can't we just get rid of the minus X on the denominator? Why don't we do that? Guys, we know what X is. Just plug it in. Just plug it in. What's the point of removing the minus x, making an approximation. The point when we do that is to avoid using the quadratic formula. So if you remove that x in the denominator, you're literally just being lazy and not subtracting that number. We know what x is, so there's no reason to make an approximation here. So we can solve that easily in our calculator, and yes, you get that this acid has a K value of 1.8 times 10 to the negative 4. This is no different than chapter 15, no different. Honestly, it's easier because everything's a 1-to-1 ratio. All right, so let's do a type 2. Type 2, right? Involving a weak acid. Do type 2 quadratic or type 2 ice tables require the quadratic sometimes? Yes, they do. So the type 2 I mentioned is when I give you initial concentrations, I give you K, and I ask you what are equilibrium concentration. So in those types of questions where I give you K and ask you to calculate equilibrium, you do sometimes need to use the quadratic formula. So let's look at this. All right, so let's take acetic acid, calculate its pH given this concentration. So pH, in order to calculate pH, I need the H plus concentration at equilibrium. So I need the equilibrium line. So the first thing we need here is a balanced equation for a weak acid. You need to get very comfortable doing this. So a weak acid, when it behaves like a weak acid, I'm just going to call this HA, a generic weak acid, has an equilibrium, it donates a proton, and then you get its conjugate base there as well. That is our Ka expression for any weak acid, right? And then you can write the Ka expression is whatever, all right? H plus times A minus over HA. All right, so we're gonna need to write out a nice table. So let's look at this initial concentration, 0.3 molarity acetic acid. That is going to go in the initial line. So 0.3. We have 0 amount of our products. Which way does this reaction have to go? Forward. So minus x, plus x, plus x. So at equilibrium, we have 0.300 minus x, x amount of H plus, x amount of HA. All of this is aqueous, all of this is homogeneous equilibrium, so that entire equilibrium line is going to go into the Ka expression. So we plug that into Ka. So we get our numerator is what? X squared over 0.3 minus x. Do we know what this is equal to? Yes, we do. It was given in the question. I told you that Ka equals 1.8 times 10 to the negative 5. Can we solve that? Yes, with a quadratic, but do you want to use the quadratic? No. Do you want to use an approximation? Probably. So let's use the most appropriate approximation here. Let's think about this. K, is it a big number or a small number? Small. So does this reaction go forward that much? No. So minus x is going to be what? A big number or a small number? Small number. So if I take 0.3 minus a small number, what is the most appropriate approximation that we can make? That 0.3 minus x is basically just equal to 0.3, whatever, right? Because minus x is going to be real small. That's small. All right, so we can simplify this as x squared over 0.3 equals 1.8 times 10 to the negative 5. All right, does that require the quadratic? No, you can just type that in your calculator, take the square root, right? So that calculation is straightforward. You get x equals, dang it, I didn't do it, 0.8e negative 5 times 0.3. Square root that. I get x is equal to 0.00735. Is that my answer? No. What does that answer represent? X is equal to what according to the ice table? Concentration of H plus. And is that what we want? Almost. Almost. What's the last step we got to do? Yeah, we got to do the negative log. So this is my concentration of H plus. And so to get pH, I take negative log of that number. and I get 2.13, 3 sig figs, so 3.4 probably. Oh wait, why is my pH weird? My concentration's not right? What did I do wrong? 1.8 E negative 5, oh my gosh. 1.8 E negative 5 times 0.3, that's why. Okay, yes, my concentration is 0.00232, is that right? Yes, okay, then you negative log that, and now you get a pH of 2.63. The concentration has 3 sig figs, but Ka only has 2 sig figs, so the pH should probably only have 2 sig figs. But let's use our intuition a little bit. What did you put into the water? An acid. So the pH that we calculate should be acidic, and is that what we calculated? Yes. And so the last idea here is I can ask pH, but I can also ask percent ionization. So percent ionization uses the exact same numbers, where we can say, oh, how much does the reaction go forward? Percent ionization is the concentration of H plus at equilibrium over your initial concentration. So what we want to do here to get your percent ionization is take that X value and then take your initial acid concentration and multiply by 100, and you'll get your percent ionization. All right, so that's just another way to represent how acidic this solution is. All right, so have a great weekend. Study, study, study. Review session is next Tuesday.